Let me talk about the mechanical behavior of conductors. And I think in the mechanical behavior, we always are concerned with the stress and the strain, for example, in a conductor. If you look at ACSR, which is steel combined with hard aluminum, they have a pretty sharp, there's a slight curve here. Let's say I'll call this ACSR. You can use what is called linear approximation in stress strain. And quite a few countries still use that in their sag-tension design. And what needs to be kept in mind is when you are working with some of the newer conductor, advanced conductor, the stress strain behavior is actually very different, okay? And this is where we have to be careful about. If I were to draw out stress strain curve or stress strain behavior for some advanced conductors, it might be something like that, its strength might be higher. And these are what I would call breaking strengths, right? Let's say we use that as TS, and this is for ACSR. These are breaking strengths. And the rated strengths normally are a little bit less. Okay, in TS conductor case, we normally have reserve strengths like 10 to 15% margin of safety there. So your actual strengths versus your rated strengths, there is that margins. ACSR, you normally don't have that much of a margin. They've been around for all these years. What is different is you do not have that linear stress strain curve. So we have to use what is called polynomials to approximate how the stress and strain is behaving. And this is fundamentally important for sag-tension analysis in conductors, especially the newer conductors. For countries that are still using linear model, they need to consider polynomial relationship for stress strain in sag and sag-tension analysis. If you were to look at some of the, let's say, earlier generation advanced conductor, the modulus is a little bit less. The curve might be a little bit different. I would say first gen advanced conductor. Why? The aluminum may behave similar, but the composite core, if I look at the slope, it's got a lower value, which is the modulus, simply because when you have a lot of fiberglass in it, it robs down the modulus of the carbon fiber composite. So if you were to, under certain ice condition, which will drive the tension in the conductor, you look at under the same tension, how much these conductors might sag. ACSR actually do pretty well because the steel having a pretty high stiffness there. And the TS conductor does have a very decent modulus. So it will sag a little bit more compared to the conventional conductor. However, our overall sag is still substantially less than the SOMO sag in the traditional conductor, and that's why you are able to handle the ice load sag. But if you look at the first generation conductor, because of the low modulus in the core, they will have significantly more sag. And that often limits the applications. This is why the first generation advanced conductor, they're just not adequate for very long span applications, heavy ice regions, and also if you have a lot of wind, that the blowout might be a concern as well.